Can you see my screen?
Yes, ma'am.
Okay. So we'll start with a fairly simple question. Um, we saw an NFA for the set of strings over 0, 1 such that the fifth last symbol of W is 1. So now I'm asking for the NFA that accepts all strings such that the second last symbol is 1, and then the main part is converting this NFA to a DFA using subset construction. So can somebody give me the NFA?
In the start state, we have a uh, loop for 0, 1 and an edge for 1, and then we have an edge for 0, 1. This one.
Okay. So this is the NFA. Now can you convert it to a DFA using the subset construction procedure? So I'll just name them PQR. And I want an M. Let's call this Q. So sigma will just be 0, 1. So you have to specify these things.
Q will be the power set of P, Q, R.
Okay, so that means empty set and then no. Okay, so this is Q. What will S be?
Singleton set P. Singleton set P.
Yes. And F?
R, P, R, Q, R, P, Q, R. All of those sets.
So all the subsets which contain there is a single final state. So all the subsets that contain R. Now for the delta function, I'll just put in these states. Let me just write it as phi P Q R and then okay, so please tell me the edges for 0 and 1. So from P, if I read 0, from singleton set P, if I read 0.
I stay at P.
If I read 1,
I go to P, Q.
the state corresponding to P, Q. Okay. If I read from Q, if I read 0.
I go to R.
And if I read 1.
Then also I go to R.
From R, if I read 0.
It goes to null.
And if I read 1,
Then again null.
okay. Then comes PQ. PQ for 0.
It will be P, comma R.
P comma R. Okay. For 1,
It will be P, comma Q, comma R.
QR. For 0,
It will be R.
R. Okay. For 1,
R.
PR. For 0,
P.
for 1,
PQ.
okay. And then finally PQR for 0. Not finally. For PQR for 0.
PR.
For 1,
PQR.
okay. Are we done?
No, for the null, we haven't
Huh.
done anything.
For null, what happens?
We
For,
loop.
for 0 or 1, we loop.
We loop.
Okay. So now, is there any state where which is not reachable? Do you think there is any state which is not reachable? Okay. So before that, this is the start state, right? And this is
Yes,
a
ma'am.
so currently this is the start state, and the final states are all the states that have that correspond to subsets containing R. Okay. Now, can you give an example of a state which is not required? Even if I remove that state, it will not affect the
Q.
language that is right.
Q,
Q,
QR.
comma R.
Okay. So I'm just marking it like this: Q, Q comma R. Anything else?
Only R.
Only R. Okay. You'll have to give me reasons. I'm just marking it for now.
And for R, we can go from Q and Q, comma R, and both of those are unreachable.
Right. So, okay. So the idea is this: Q does not have any incoming edges. So in particular, it cannot have any path from the start state P to Q. So if I removed Q, then that will not affect, even if Q reaches a final state, that will not affect any of the languages, any of the strings that are being accepted, because all the strings must have a path. This is a DFA, so the strings being accepted must have a path, one single path labeled by that string, ending at a final state, but it must start at the start state. Q is not reachable. The state corresponding to Q, this is not reachable from the start state. Similarly, this state QR, despite being a final state, is not reachable from the start state. And as one of you pointed out, R is only reachable from from Q and QR, which are not reachable from the start state. So R is also redundant. Anything else?
The null set.
Null.
The null set. The null set is reachable only from R. So it cannot, by continuing our argument, it cannot be reached by P. Okay, is there anything else? No, right? Others, everything is connected to P. So see, this construction, we took Q to be the power set of P, Q, and R, but when we construct the DFA, we see that there are some states which are redundant, which need not, which are not necessary. They form, if you consider it in terms of graphs, they form a separate component. They do not belong to the same connected component as P. In this case, they do not belong to the same connected component as P. In other cases, I think you will be able. Do you know what strongly connected components are?
Yes, ma'am.
Okay, so try to relate it to connected components and strongly connected components. So okay, so I think you know that in a graph you can decompose a graph into a tree. You can think of a graph as a forest where each node, if you consider a connected component of the forest, it's a tree. Each node of that tree is a strongly connected component. Do you know this? Have you studied this in algorithms? Otherwise, we'll discontinue this line of thought. Do you know this?
Can you repeat the statement?
So I'm saying for a strongly connected, if I give you a directed graph, need not be connected. It will be it will be like a I can think of it as a directed forest where each component, if you look at each component of the directed forest, that corresponds to, each component is a directed tree. Now, each vertex of the tree corresponds to a strongly connected component of a component of the directed graph. You have the directed graph. Okay, I don't think you are familiar with this.
Ma'am, it need not be a tree, ma'am. It can be a DAG also, right?
So directed tree. It can be a DAG also, right? It can be a directed acyclic graph. Yes, each of the components is a directed
No, you're talking
acyclic.
about the condensation graph, right?
Yeah, I think it's called the condensation graph.
Yes. No, it can be a DAG.
It can be a DAG. Each component can be a connected DAG. And each such node corresponds to a strongly connected component of the given directed graph. If you are familiar with this, then try to think of look at each of these components. Which of them can you discard? Look at each of these nodes. Which of them can you discard by this argument?
Ma'am,
Yes?
this was skipped in our course.
Okay, those of you who know, you can think of it in this term as well. Those of you who don't know, you can forget it. A graph can be thought of as um, a directed graph can be thought of in terms of uh, a set of, or you can think of it as a DAG where each connected component of the DAG, consider a connected component of the DAG that corresponds to a connected component of the original directed graph. Now, in this connected component of the DAG, each vertex corresponds to a strongly connected component of that component of the original directed graph. Those of you who know this, try to think of which of these components can you discard in terms of if the original graph was the directed graph corresponding to the transition diagram of a DFA. And those of you who don't know it, forget it. Okay, so we saw an explicit construction of explicit application of the subset construction procedure for an NFA to construct a DFA. And we also saw that there are certain, in this example, there were certain states which are non-reachable from P. And therefore, they can be, they can be discarded. They are redundant states. They can be discarded to get a smaller DFA accepting the same language. Okay, I'll skip this question. Now I come to a generalization of the question I left you with last class. So let k be a positive integer constant. It's a constant and it's also a positive integer. L is the language W belonging to 0, 1 star such that the kth last symbol of W is 1. We saw the example in terms of the fifth last element. And the question was, prove that no DFA with less than 2 to the k states can accept L. And I've added another part that no NFA with less than k plus 1 states can accept L. So how will you prove it?
Ma'am, for the A part, we can, ma'am, for the sake of contradiction, we can assume that the number of nodes for a DFA is less than 2 to the power k.
Okay, so suppose size of Q is less than 2 to the k.
And then we can consider the set of all k length binary strings 0, 1 to the power k.
Consider all k length strings in in 0, 1 star. Yeah.
Ma'am, so there will be two distinct such strings which will get mapped to the same state.
Mapped to I will just okay let me just say x comma y x comma y ending at the same state. Let's call it something p.
So
Then we can add zeros. Like we find which one of where the strings differ, and then we add zeros such that one of them should be accepted and one of them should not be. But
So
as they were
the
in the
strings can
same
differ
final
in more
state,
than one places. Which one are you
yeah,
considering?
the last one,
Last from the right.
the last one
Okay,
on
the
the
last one.
right.
Sorry, so the first one from the right. Look at the first place from the
Yeah.
right, where x and y are differing. So without loss
Yes.
of generality, I am assuming that x has 0, y has 1.
Yes, and we start adding zeros to the right.
So let's just assume that this length is I.
And we will add k minus I zeros to the right of both of them.
Okay.
Not k minus 1 minus I, because k
Right,
last
right.
symbol.
Yeah.
And but they were in the same state, so they will be in the same state after all of this.
Why?
They were initially at the same state, let's say P, but
So
and
suppose they were
it
at
was a
S,
DFA.
they took two different some path like this and reached P.
Yes, ma'am. And now we are just adding zeros. They are in the same path, and we are getting the same string 0 0 0 0. So they will be on the same path
Okay.
and reach the same
So
state.
basically from P, if I take the same substring, then there is a unique path, so I will reach the same state, some Q.
Yes, ma'am. But
Okay.
for one, this should be a final state, and for the other one, this should not be. So
So
there's a contradiction.
X should be rejected and Y should be accepted because
Yes.
the kth last element is of Y is 1 but of X is 0. So
Yes, ma'am.
therefore, I mean, it didn't have to be all zeros. It could have been any k minus I minus 1 length string. I just
Yes.
keep the same string, and X would have been rejected and Y would have been accepted. This particular string from P will be unique, will correspond to a uniquely labeled path labeled by this string reaching the same state. So so this I will call X dash, the new string I will call X dash, and I will call Y dash. X dash and Y dash starting from S reach the same state Q if I have less than 2 to the k states. There exists a X dash and Y dash which reach the same state Q, whereas X dash should have been rejected while Y dash should have been accepted. Anybody has any doubts regarding the proof?
Ma'am, at what point do they reach P? Means during which?
So they reach delta hat Sx is equal to delta hat Sy is equal to P. And then delta hat Sx alpha. So this alpha I am just writing as 0 to the k minus I minus 1 is equal to delta hat Sy. I'm concatenating the same string, and this reaches Q. Both of them will reach Q.
Yes, ma'am, got it.
Okay.
Ma'am, if possible, like where are we exactly using the fact that mod of q is less than 2 per k? Could you explain that?
Mod of Q less than 2 power K. So how many K length strings can there be? Over here. How many
Okay.
K length strings can there be? 2 power K.
2 per k. Yes, ma'am, got it now.
Right. So this is where what is the principle we are using here to give this statement?
Weakened principle.
Right, right. Okay. So then let's move on to part B, where you have to prove that no NFA. So we saw an NFA with k plus 1 states accepting this language L. We saw it for when k was equal to 5, but we know how to construct an NFA with k plus 1 states. The question is, can you prove that we cannot reduce the number of states and accept the same language by any NFA? So now for NFAs, you don't have single paths. You can have multiple paths. So let me just assume that Q is less than K plus 1. So I'll just write it as less than equal to K, which just means that there are 2 to the K subsets of Q. Okay, now can you do something? Can you do something similar to this?
Like if we find some unreachable states, then it is done, right?
Some unreachable states.
Yeah, in the 2 to the power k, if we see that there will be some unreachable states, then the number of reachable states is less than 2 to the power k, and we are done.
I did not
But
understand.
like in these 2 to the power k subsets, we create a DFA, and if we find that there is some unreachable state, and then the number of states has decreased, so we are done there. But if it is exactly 2 to the power k, then there
Oh,
is
okay.
no.
1 minute, 1 minute. 2 to the... Okay, give me 1 minute.
Ma'am,
Yes, yes.
I think we can claim that there shouldn't be a case where the path takes it to 5.
Takes it to?
5.
Yeah, okay.
Uh,
So, okay, continue.
Because if
Is this,
there is-
just one thing, the person before, is this what you were saying by unreachable state, or that we have to show that at least one subset is unreachable? Is this what you were
Yes,
saying?
yes, ma'am.
Oh, okay, okay,
Yes,
okay.
yes, yes.
Okay, okay. Yeah, okay. So can you,
so,
so somebody
if
said
X
that let's show that phi is unreachable.
so if X is an input which leads so that it goes to the phi in the subset construction of the DFA. Uh,
Hmm.
so in that case, we can just append another k-length string with all ones, and it should remain at phi itself, but phi cannot be a final state.
Okay, so you are taking an X. Okay, so again you are considering k-length strings, right?
Yes, ma'am.
Okay, so let's start. So you have k-length strings. In 0, 1, 0, 1 star, and then your argument is suppose delta hat sx, take an x which is in this. So suppose delta hat sx is equal to phi, then I take x1 to the k,
Yes, ma'am.
and it should remain in phi itself. I mean it should not be going anywhere else. This should be, if delta hat sx is phi, then delta hat sx1 to the k is also phi, and this is a contradiction because this should be accepted. Is this point clear to the others?
Yes, ma'am.
Okay.
No, ma'am.
Okay. Okay.
Ma'am, I am unable to understand like how this proved that.
Okay. So delta hat sx is phi, meaning that if I take any x 1 to the k is a string. So x is a prefix of x 1 to the k. If delta hat sx is phi, then delta hat sx1 to the k is phi. Can you tell me why?
Ma'am, why are we supposing that delta cap Sx is phi?
No. This is my statement. Prove the next. This is my statement. Assume this.
Yeah, ma'am. Then
After that, can you prove this statement?
yes, ma'am.
Okay. Who was asking the question? Somebody said they did not understand.
Ma'am, me, I was asking.
Yeah. So you assume this first. Suppose delta hat sx is phi. Can you show that for x 1 to the k, it must be that delta hat s x 1 to the k is phi, which is a contradiction because x 1 to the k should belong to the language. Can you show that if I take anything appended to x where delta hat sx is phi, then delta hat sx so let's say y was appended, delta hat sxy will be phi from definition of delta hat.
Yes, ma'am, because it is phi means delta hat of sx into 1 means y into y. So phi into y would be phi because y is k-length string. Yes, ma'am, got it.
Or if you consider in terms of the transition diagram, this phi delta hat was representing all those end states for paths labeled by x. There is no such end state. So you cannot extend any path with this y which was appended. Okay, so now this for this assumption, we know, if we assume this, we know there is a contradiction, which means that phi is an unreachable state, as somebody was pointing out. We have found out an unreachable state. Now, whoever said if we find an unreachable state, then we are done, please now continue with the proof.
Yes, ma'am. Given that there are only 2 to the power k or less subsets, and we have found one, so now
K
the
minus 1.
corresponding DFA will not have enough states.
Okay. So now you consider the DFA with subset construction.
Yes, ma'am.
Or you can just directly, this is one way, or just directly, suppose I have two strings x and y such that delta hat sx is equal to delta hat sy is equal to, let's say, some subset s hat, let's say. Now, if I, for all z, can I say this delta hat sxz is equal to delta hat syz?
Yes, ma'am. The proof we did earlier with the DFA.
Yeah, but this we did earlier with the DFA.
Yeah,
But
the 2 to the power k one.
Induction
This
on
is the same one,
multiple
right?
No, but now you can have more than one path.
Like for the subset construction, we cannot.
No, but forget the subset construction. Even in the NFA, if I reach, so I have S and I have S hat. So I will take two colors.
Yeah,
Okay,
I
so these are the
understood.
paths for
If they
X.
go to the same set.
And I have some other path. I have something else. It could be different number of paths. It could behave differently, but the endpoints are the same. So now from this subset, it's the same subset, right? Now from this subset, if I look at the number of paths labeled by Z, however they are, they will be reaching the same set.
Yeah. Yeah, understood.
Okay, so then this point, this will be true. So even if you visualize it in the NFA, this will be true. Okay, can we move to the next question? Or someone has a doubt? Okay, so another kind of easy question. A and B are regular languages. You have to prove that A sim B, which is A minus B union B minus A. This is also regular. So how will you prove this?
When we can write A minus B as A intersection not B.
Okay, so then
And
similarly.
yes, ma'am.
Okay, now anybody has any doubts about why this will not be regular? About why? Does everybody understand that this will be regular?
Yes, ma'am.
Okay.
And all of A, not B, B and not A are regular.
Correct. So this is regular, A, B, not A, all these are regular. So this will be regular because it's closed under intersection. Similarly this, and then the whole thing will be regular because regular sets are closed under unions. Okay, can I move to the next question? Anybody has any doubts? Okay, I'm moving to the next question. Okay, so now A is a regular language over 0, 1. 0, 1 are the input symbols. Then you have to prove that the language B, which is XY belonging to 0, 1 star, such that X1Y belongs to A is regular. So if I draw a schematic diagram, so you have, let's say I have a DFA for A. So you have a start state and then you have some final states, and xy is of the form x1y is, let's say, some x is labeled, the label path x reaches p, and then you have a 1 which reaches q, and then the label path y reaches some final state. Okay, so this is the schematic diagram of any x1y that belongs to A. Now you have to give me a DFA or an NFA such that xy, the strings xy where x1y belongs to A are accepted. So what can you do? You don't know the position of this 1, right?
Ma'am, can we merge P and Q?
Merge P and Q, but P and Q can have other things coming in. There could be something going into Q which is not coming into P. You may lose out some strings if you merge P and Q. You don't know exactly what P and Q is. If you want to merge every string, every edge that is labeled by 1, then you may collapse the entire thing and accept something completely different.
Ma'am, if this is one NFA for A, and we can make a size of q copies of it, and we can, for each copy, we can loop one for a particular vertex. So it will be the NFA for the set A union B.
So just for one copy, let's say this copy is for P, what are you doing? You're looping one where?
From P to P for the alphabet one.
But then you will accept different kinds of languages, right?
And then the accepted language would be A union B.
A union B.
Yes, ma'am.
Wait, no, once more. What will be A union B? If I take Q copies of this, one for, let's say, one for P1, one for P2.
Okay, ma'am. No, ma'am. This loop can be traversed multiple times.
Yeah, exactly. I will be accepting something completely different. And also your line of argument, okay, so suppose I construct something for A union B.
Then I was thinking of taking a symmetry difference with A, and
Okay.
then again union with.
Okay, I have to think whether even that
Yes, ma'am.
works.
It doesn't fully work.
But so you don't know where exactly this 1 is going to appear. It's not that you can collapse or get rid of a 1, because this, I mean, this 1 1 1 1 could be accepted, in which case like 3 1s will also be in the language B. So suppose 1 1 1 1 is in A, then 1, 1, 1 is in B. So if I collapse or delete ones, then I will not be able to accept. I mean, I cannot collapse or delete ones because I will not be accepting 1, 1, 1 in B.
Ma'am, can we make an epsilon transition?
Okay, so meaning you are trying to guess where this 1 is.
Yes, ma'am.
So what are you making? So epsilon transition 2? Oh, you're saying instead of 1?
Yes, ma'am. Instead of 1, right?
No. Then I think you will also be accepting x1, y, right?
No, it will be the same thing as collapsing this.
I think so. Same as collapsing. No, it won't be the same as collapsing. You are accepting A and you're also accepting B. I think this will be, I think you will also accept more things. Even if A and B do not have any epsilon, you will accept the epsilon path because this is a DFA. I'm starting with a DFA. Every vertex has a 1. So everywhere you're including an epsilon transition. I think you may end up accepting epsilon even if epsilon is not in A or B. But can you use this epsilon transition to guess where this 1 is?
Ma'am, I'm not getting what do you mean by guessing by this epsilon transition?
No, I'm not saying this particular epsilon transition. This may not work.
Ma'am, the epsilon transition you drew, like that NFA would give the language as A union B, right?
I think it can give more things. Suppose A and B do not have epsilon, but but each of these things have a 1. Then I think you will be for every edge labeled 1, you're adding a corresponding epsilon. So I think you will also be accepting epsilon. But maybe if each edge has a 1, yeah, I don't know. I'll have to think about it. I don't even know whether if I put an epsilon instead of these ones, whether A union B is accepted or you can accept something more. But definitely B is not accepted. You can also accept things from A.
I mean, if we could prove A union B is a regular language and A is already a regular language, then like we can use the symmetric differencing, right?
Okay, so what are you saying? A union B, symmetric difference B is?
Ma'am, symmetric difference A.
Symmetric difference A. So that will be A intersection A union B minus A union A minus A union B. So this would be A union
A minus B.
This is A minus B. Why?
Ma'am, overall it would be शायद B minus A.
Okay, ma'am. The second argument is A or B.
A minus A union B. What will this be?
5.
Can we do this? A
Null.
minus A union B.
But 1 minute. Somebody said what is A minus A union B? Somebody gave some answer.
Ma'am, this is 5.
5.
It's null, man.
Null.
Okay. So somebody is saying if you can construct A union B, then you take A union B, symmetric difference A.
Why is the first argument equal to A?
No,
So
it is
why is
B
the
minus
first
A.
argument equal to A? A union B minus A will be, oh, okay, sorry. This is B, yeah. If so, somebody is saying, sorry, this will be B. Somebody is saying if you take,
right?
Ma'am, B minus A.
And because A and B are not guaranteed to be destroyed.
it will be B minus A. That's also true.
Yes, ma'am, that's the mistake I was making. I was assuming that it will be B, then like we can prove regular sets.
Yeah.
Ma'am, can we do like this, like from P to Q, we make it like either we get 0 or we get 1, we go from P to Q, and all the final states we go to a pre-final state.
I did not understand. From at P, if I get 0 or 1, what do I do?
I go to Q.
Okay.
And for all the final states, I make the pre-final states as the final states.
Yeah, you have to prove why this is correct, because you may be accepting something much more than B. So now you are including an extra 0, right? So those things, so now x0y is also being accepted. It may not have been accepted earlier.
No, ma'am, x0y would be a length more than that. Like we have made all the final states, we have made the pre-final states at the final.
No, but then x11y will also be in, suppose x11y was in A, then x1y was also in B. You cannot guarantee that this is the maximum length of a string that is being accepted. And you don't know where this is exactly. Can you exploit that? You don't know where this one is happening.
Ma'am, even like it might even be that the like from the pre-final state to final state, it goes only if we get a 1 or something. Like suppose if it was, if
So
you
I
only
think
get,
he is saying you introduce a 0 or something. I don't think this will work. Okay, so let me give you a hint. So you have the start state over here. I make a copy of this. So if this was M, I take M1 and M2. And if there was a P, I take a P dash over here. Okay. Now, whatever were the final states up there, I don't keep final states in M1. I keep final states in M2. Same as M. Now, if there was a transition, a one transition from P to Q.
And then we can make an epsilon transition from P to Q prime.
Correct. Then we make an epsilon transition from P to Q. If there was a loop from P to P itself with 1.
An epsilon transition from P to P prime.
Correct. Okay, so the idea is that you are, with these epsilon transitions, you are guessing where this one is going to happen, because you don't know. You don't know how this string, you don't know explicitly what strings belong to A. You just know that A is regular. You don't know exactly where this one appears, such that I mean, if x1y was a certificate that xy belongs to B, you don't exactly know what this x1, y is and where this 1 appears. So instead of fixing where this 1 appears, we design an NFA that guesses where this 1 is happening. And if this, wherever this 1 happens, I move wherever this 1 occurs, I move from the first copy to the second copy and continue in the second copy. Okay, so instead of 1, I make an epsilon transition to the second copy and read the set. So suppose I had an x that was reaching P, and okay, so here suppose I had the x that reached P and then with a 1 went to Q and then went to Y. So now from Q dash I follow the path corresponding to Y and reach a final state, this exact same final state. So can you prove?
From all states in M1, we have to make epsilon transition to M2.
Not from all states. From all states, sure, from all states, but in a particular manner. So this epsilon transition, suppose P, so from every state there is an edge labeled 1 going to another state. So for every P, for every P in M, there is an edge labeled 1, exactly one edge labeled 1 going to another state Q. So we make the epsilon transition from P to that Q. This Q could be same as P.
Yes, ma'am.
Yeah. Now prove. Now you have to prove. I made a diagram. You have to prove why this will accept B and nothing else.
Ma'am, for one direction, we assume that for a string in B, if we can insert a 1 somewhere, then we can just replace that 1 with an epsilon transition and it will form a valid path in this constructed NFA.
Okay, wait. String in B.
Yes.
Huh?
So
for a string in B.
So, ma'am, let's say for x comma xy in B, such that x1 y is in A.
Okay, so for xy in B, it is in B because there exists an x1 y in A. Right?
Yes, ma'am.
Okay.
Ma'am, so in the transition, so if there was a path S, S1, S2, S3 up to some Sn, such that Sn belongs to F in the original DFA for A.
S1 to Sn in M such that Sn belongs to F.
And let's say the transition for 1 occurs from Si to Si plus 1.
Okay.
So the string that corresponds to xy in M1 and M2 is S1 up to Si, then Si plus 1 dash up to Sn dash.
Right, and Sn dash belongs to this new, I'll call this Fm dash. Okay, so he has displayed a path in the new NFA such that this path accepts xy if xy belongs to B. If xy belongs to B, it must be because there exists a x1y belonging to A. That means look at the path labeled by x1y starting from S in the DFA M. That will look something like S1 to Sn, where Sn is the final state. Now, suppose X was labeled by the X. Suppose X labeled the subpath S to Si. Then Si1 was labeled by 1, and then Si1 to Sn was labeled by Y. So then from Si, I take Si plus 1 dash to Sn dash. There was an epsilon transition here, which means that in my new NFA, I have a path labeled by xy starting from the start state and starting from a start state. Here it is just one start state and ending in a final state. Other direction, suppose suppose Z is accepted.
Since there cannot be a path from S J dashed to Sk, because all the transitions are from M1 to M2 or M1 to M1 itself or M2 to M2 itself. So we can assume that uh, the path looks like the above path S1 Si.
No, so the first thing is, if Z is accepted, then there exists an epsilon transition from M1 to M2. Otherwise, you are starting in M1, you cannot reach M2. Right?
Yes, ma'am.
Okay. Now, what is this epsilon transition? Let's say it goes from P to Q dash. So by definition, that means delta M of PQ was equal to 1. Now you construct the suppose
Delta M of P1 equals Q.
Sorry. Delta M of P1 equals Q. So now if you consider the acceptance path, there must be at least one acceptance path. So let it be S1, 2, and then you have P, Q dash, and then some final state F. So you construct S1, P, Q, F. This will be accepting X, 1, Y in M. And this is accepting XY. So therefore, any Z that is accepted must be of the form XY such that X1Y is accepted in M. Fine? Okay, so I think we have to stop here. We'll continue with the other exercises. Do you want me to upload the entire thing with all the exercises given? Or
Yes, ma'am. Please upload it.
okay, so there is one more question that I skipped. The second question. There are a few things where you have to show whether the set is regular or not. There is one more question that I skipped. Consider the following NFA epsilon transition for the language. NFA with the epsilon transition for the language L A I B J. So this is the NFA, and think of what can be a DFA accepting the same language. So I want to get rid of this epsilon transition. Think of how you can do it. One other comment I wanted to make. So somebody wanted to prove using this that if I have A union B to be regular and A to be regular, he wanted to show whether B is regular or not. So I want you to think about this. Okay, so at some point we will, maybe in the next week, we will be learning about how to show whether a language is regular or not. There will be examples of languages which are non-regular, but you have a basic idea that there must exist languages which cannot have finite machine encodings. We have seen this in the first class, the second class, and so on. So there must exist an A prime subset of sigma star such that no FA exists for A prime. Because the number of subsets is uncountable, and we saw that there are countably many finite automata, let's say countably many deterministic finite automata, because we can encode them as a finite string. Okay, so now suppose I take sigma star minus A prime to be B and A to be A prime. Can you tell me what sigma star is? Is it regular? Sigma star?
Yes, ma'am, regular.
Why?
Because the singleton
yeah,
NFA
sigma star is just this. Sorry, this this is a DFA for sigma star. Sorry, not AB. Yeah. This is a DFA for sigma star. So sigma star, so if A union B so A union B here is sigma star, which is regular. B is sigma star minus A. Okay, I won't, yeah, I don't think I can give you the example immediately. I think you think about this. We know that there exists languages which cannot be accepted by finite automata. You think about whether this is true or not. A union B is regular, A is regular, can you show whether B is regular or not? Is this statement true? Okay, so I will upload this set of problems, and yeah, I think we'll end the class here today. You can try the problems. We'll revisit it in the next tutorial. Okay, thank you.